Okay, so remember I had a video at the very beginning introducing the question of can we um, construct a length function that behaves nicely on all the subsets of the real line? And the answer is no, as we just saw. Um, or rather, we didn't, my apologies, we didn't prove that the answer is no. What we did was we showed that Lebesgue outer measure, or just outer measure, does not behave nicely on all subsets. In particular, there exist two disjoint subsets A and B, where the outer measure of A disjoint union B is not the outer measure of A plus the outer measure of B. So what I want to do in this video is actually prove, and it's very easy given the last video. I want to prove that there does not exist a nice length function on all of the real lines. So in particular, I want to prove the following. Yeah, and this uses it's all almost we've almost proved this actually. Um, there not exist. Let's call it capital M. Better to call. We don't want to call it little m. Yeah, so I've taught this course many times, and this is the first time I stated this question, does it exist? And I said, well, you can prove it. And yeah, this is the first time I've actually did it in class. Um, we can actually state something a little well, not that much more. So there does not exist capital M where this is one, this is countably additive. That for all disjoint, pairwise disjoint subsets of the real line. Now with it, well, let me finish this and then we'll discuss this in a second. So again, this is these are pairwise disjoint subsets of the real line. And C, this is translation invariant. And I'll ask variations of this and give answers as best I can, as best there is. That E is a subset of the real line, and X, and okay, so and so to be clear, when I write this, I mean, this could be actually finite. This could be, so we have a countably infinite number of the EKs or a finite number of the EKs. So um, for all disjoint finite number of EKs or countably infinite number of the EKs, this is right. Um, Yeah, so now we need some properties of this M function to prove this. The proof is basically going to be the Vitali kind of construction that we did in the last video. Um, so I will use that, but I won't prove the things we did in the last video. But yeah, let's assume M exists Now let me prove some basic properties. M, if so, these are easy properties. So first, we have countable subadditivity. So yeah. So let's say I have a again countably infinite number of, let's say, AKs or a finite number of AKs. Given we do this jointification process. Okay. Yeah. Yeah. Well, let's say we're given not necessarily a disjoint EKs. Be clear, not necessarily pairwise. That okay, so remember what the disjointification process is. The way I like to do it, because it's very intuitive, is you do this in two steps. You first kind of, in an obvious way, come up with an increasing or non-decreasing sequence of sequence of sets. I equals 1 to k I. All right, and set ek tilde to be kind of the pieces of the onion essentially. Go back if you want to see the pictures for these. Go back to video. Get which video it is. Um, Either measurable sets part 1 or part 2. Okay, now the thing is, to remember, these are pairwise disjoint. So this disjoint union, and square bracket, is going to be the union of the original EK. All right, so the big thing though is that I want to know that each one of these is a subset of EK. That's easy. Because this here is going to be equal to, just plug in for what, squeeze this in, plug in for what EK is. This union here. Okay. Take away, not going to do a bracket. I. EI. Okay, and basic set theory. This is going to be baby set theory. EI take away each union. Well, this is empty unless yeah, this is going to be empty unless I equals k. So this is going to be equal to ek. And if you have any doubts, check this yourself. Um, I equals 1. Well, it's pretty obvious. Because if I is not k, then we're taking away all of ei. The I is not equal to k. So it's obvious. I equals 1. 1. Again, the whole point that we needed is this is a subset of ek. All right. Ek tilde is a subset. A lot of people define the stratification process essentially just by this equals this. And again, I think pictorially, if you do it in these two steps, the picture is just so much clearer and so much more intuitive as to what is going on. Okay, so that means this union here, basically done. Going to be equal to this union here. Yeah, this is a good proof because it shows you that particularly probability measures are countably subadditive. All right, so it's countably additive because the ek tildes are pairwise disjoint, and each one, remember, is a subset of ek. Messy. But yeah, so that proves countable sub. Okay, so next basic property that we need is the following. So technically, I'm careful here. Yeah, I should be a little careful here, actually, because this is something we need to prove. So in particular, this is true for any A is a subset of B, but so E particular K you can write as the obvious thing. EK takeaway, EK tilde, this joint union, E tilde. So any property that you use that's kind of obvious for a big measure, it might be true, but you got to be careful and prove it. So that means this is going to be, well, I'm not even going to write it because I don't care. But it's EK, take away EK tilde. Really nice. I guess it can't be anything else. And point is, this is bigger or equal to M of E. Okay. This. All right. So yeah, next basic property before we get to prove this is the following. Yeah, okay. That is measure of a singleton for any x. This is, well, one thing that's kind of obvious is that we just need to prove that the measure of zero is zero. I mean, you could directly work with set containing x, but assuming it's translation invariant. So this is obviously 0 plus x. So, I mean, it's true. Useful. Got a little brain fart here. So it's enough to show that this is zero. Okay. There's a million ways to do this. The easiest thing I think to do would be following. Yeah, do this. I mean, it's not the easiest. It probably isn't. Just work with a countably disjoint or pairwise disjoint collection of um, singletons that are a subset of 0 1 over k. So the set containing 1, 1/2, 1/3, et cetera, works. So it's a subset of 0 to 1. So just play around. 1 equals this measure. Yeah, I'm going to use translation invariance again. I guess there's no difference between 0. I mean, I guess just make things a little easy. Anyway, so because it's countably additive, this is going to be bigger or equal to the measure of this here, which is the following sum. Again, by translation invariance, this is the same thing as just obviously this is 0 plus 1 over k. So by translation invariance, which we are assuming, this is going to be equal to here. So it's a fairly obvious. Okay. Well, the only way we get this to add up to something less than 1, because it's infinite sum, is if this is okay, and finally, a silly thing. Not really that silly. Again, you always got to be careful. As easy as these proofs are, you got to make sure they're true. I want the big M of minus n to n for any natural number n to be 2n, and you can do that very easily. And then, yeah, we're almost done because we have the Vitali construction, and I'll kind of show you. I'll remind you of basically how it works. I mean, I never really appreciated until recently how beautiful the Vitali and how useful the Vitali construction is. I think, I don't know, the Tarsky is like pushing that idea beyond anyone's imagination. Check that out if you're interested. Um, requires a reasonable amount of group theory. I don't think anything too bad. Like a solid undergraduate group theory course works. Um, okay, yeah, so kind of do the obvious thing. Um, yeah, so one thing is kind of obvious is that, well, all right, so let's just directly work with m minus n to n. Second, one of these days I promise I'll figure out a better writing system than Microsoft Paint. There must be something. Okay, so do something kind of silly like following this disjoint union. Just do like translation and variance with this. Let's do k plus 1. Yeah, so this is going to be equal to, well, this is 0, measure of this, so just sum. And of course, this is um, 0 to 1 open plus k. Well, the measure of 0 to 1 closed open because we proved that singletons have measure 0. That's going to be just 1. So you're adding 1 up. Um, 1. Basically, you're just adding this up 2n times. We're adding 1 up 2n. Okay. Okay. Now we can finally prove, or almost, well, yeah, we can almost prove our. So the proposition that whose proof is exactly the same thing as in the prior video, and I want to emphasize that. Um, so proposition is as follows. Um, Stated a little differently, but let's say this is bounded if there exists bounded countably infinite lambda where these are pairwise disjoint. Then just like before, the conclusion is that this is, Yeah, so the proof of our main theorem is going to be like the Vitalik construction, basically, and you prove essentially like 0 equals 1, which is not true. Um, yeah, so A and same proof. This are both bounded. So this union is also so in other words, it's a subset of minus n to n for some. Okay, we're basically done. Because what this is saying is infinity going to n. Well, I'll even it's what the hell this is. It's finite. Um, yeah, so we use the properties of big M. Countably additive. Sorry, this should be lambda, not A. A. This is these are pairwise disjoint. Those are going to be the following sum. I'll use translation variance. Right, and this equals split right, but well, infinity. This is countably infinite if M of A bigger than 0, 0. If this is, but we know this is finite, it's less than 2n. So that means well, it's gotta be so measure the big M of A has to be. So we add up the same thing infinitely many times to get something finite, something non-negative. Uh, 0. Okay. Yeah, like I said, I'm not going to do everything with the Vitali construction. I'll only actually mention the properties we really need. Um, and you can go back to the previous video. All right, so this is a theorem we need to, does not exist this big N. Uh, satisfying all these. Okay, so second. Yeah, so let's just work with 0 to 1, make our life easier. I don't care which and we can do a Vitalik construction for any set of positive outer measure. So let's just make life easier and work with 0 to 1. All right, just quick review. So we say x equivalent to y, rational equivalent if x minus y is in the rational. So x is y plus the rational. And yeah, so we're going to work with the set 0 to 1. Why not? So we use the axiom of choice. Choose, yeah, just like before, one element from each distinct class X subset is 0, where X itself is in 0 to 1. Um, yeah, and place these. Remember, though, this is what we do into a set called script C, whatever. In general, some E with non-negative, non-zero out of measure. Here it's U. All right. Yeah, so what are the properties we needed? You think about it. Can go to the previous video to do this. We already proved this. I called this 3 and 4 in the previous video. I'll call it 1 and 2 here because it's really all I need. Other facts from the previous video were used to prove these facts. So 1 is if this is anything at all, subset of the rationals, countably in, sorry, if this is anything, then these are pairwise. And 2, 0 to 1 is a subset of well, this union here. Second. Yeah. I knew I was going to do it. It should be 0 to 1. I mean, E. That. should be a comma here. That. And be a little more consistent. It's a disjoint union. Okay, yeah, so we're basically done now. Um, so let's say this is it's like essentially like before the rationals intersect 0 to 1. I think this is what we did actually before in the previous video, but so this is bounded and countably infinite. So by 1, these are pairwise disjoint. Yeah, so these are pairwise disjoint. And so that means the measure of C, my A being C of 0 to 1 has to be. So what did I call this? Yeah. Again, this is countably infinite. It's bounded. One says these are pairwise disjoint. So the proposition then says the measure of whatever is here has to be 0. So here we're using big A is script C of 0 to 1. All right, well, that violates 2. Again, that gives us 0 equals 1. Um, yeah, so 1 is this measure. 0 to 1 is a subset of this here. So this is a subset of, well, it's a disjoint union by 1. So then we use translation variance. Again, same kind of thing here. Yeah, and this equals. So this whole thing here. So 1 is not less than or equal to 0. So that means there is a contradiction. All I can do possibly. And that ends the. We just proved that if such a big M exists, satisfying all these conditions that we had, big M of 0 to 1 is 1, countably additive or additive among also finite pairwise disjoint sets, and translation invariant. Then we get 0 equals, thanks to the axiom of some version or weaker version of axiom. Okay. Yeah, so I think I'll end this video and I'll do another one where we talk about basically going beyond this, going further, and just asking a few more interesting questions because definitely this is not the end of the story here. What if we just ask for A and B and we don't demand C? What can we say about such an M? And we can say a lot, actually. Or sorry, um, does such an M exist? And the answer is it's actually not clear. But what you could prove is that if M satisfies A and B, then for Lebesgue measurable sets, big M here has to coincide with Lebesgue measure. And you can also ask, well, what about just A and C? What if we just uh, actually before I yeah, let me before I say something that's wrong, let me end the video and we'll talk about stuff.